Number 3. You have a beam of protons accelerated from rest through a potential difference of 0.745 kilovolts, which then enters a uniform magnetic field perpendicular to the direction of motion. What size magnetic field do we need if we want this beam to go in an arc of radius 1.75 meters? Well, if we start with a proton, I'll just say traveling to the right, velocity v, and then I'll take a magnetic field perpendicular to the direction of motion. I'll just say into the page. Then, as this proton travels this way, v cross b will give up, so its trajectory will start to do this. And it's that radius here that we want 1.75 meters. But we need to know how big this magnetic field needs to be to do that. So, in this magnetic field, we have a magnetic force, Q VB sine theta, and that force is causing this proton to accelerate, and it looks like that force will be in the centripetal direction. So MA, A will be centripetal acceleration, v squared over r. So this v and that cancel. Since the magnetic field and the velocity are perpendicular, theta is 0 and sine of theta is 1. So we get QB is equal to mb over r. Then we need to solve for b. So that gives mv over qr. So we know the mass of a proton, we know the charge of a proton, and we know the radius of the trajectory that we want, but we do not know this v. However, it says these protons are accelerated from rest, so v initial is 0, through a potential difference of 0.745 kilovolts. So if I know the difference in electric potential, and I know the charge, which we do since it's a proton, then I should be able to find the change in potential energy of this thing. Q is 1.6 times 10 to the minus 19. Delta V, well, now when you think about it for a minute, this proton is going to be accelerated in the same direction as the electric field. And if it's going in the same direction as the field, since the electric field points, well, toward decreasing potential, this change in potential should actually be negative. 745, and then kilo is 10 to the third. So I have a change in potential energy of minus 1.192 times 10 to the minus 16th joules for each of the protons in this beam. Now, what does that mean about the final energy? Well, change in kinetic energy, that'll increase by this same amount, 1.192 times 10 to the minus 16th joules. If the initial velocity is 0, initial kinetic energy is 0, so this will just be 1/2 m, which is 1.67 times 10 to the minus 27th for a proton. V final squared minus, well, again, the initial kinetic energy would be 0 because they're starting from rest. Therefore, the velocity of this proton after acceleration is 3.78 times 10 to the 5th meters per second. Now we can use our expression for B, m 1.67 times 10 to the minus 27th, v, which we just calculated, 3.78 times 10 to the 5th, divided by q, 1.6 times 10 to the minus 19th, times r, which we want to be 1.75 meters. And if you put that into a calculator, you find 2.25 times 10 to the minus 3 Tesla, or 2.25 millitesla. That magnetic field should make those protons accelerate in a circle of radius 1.75 meters. Then, Part B asks, what happens if instead of protons we use electrons? Well, I guess one thing, if the field is still pointing in, V cross B will be up, but if this is a negative charge, the trajectory will be in the other direction. But that's not what the question asks. They want to know if we want the radius to be the same. So again, this radius here, even though it's on the other side, we want that radius to still be 1.75 meters. So what do we have to do to the magnetic field to produce that trajectory? Now, I guess there's two ways you could do this. One, go back and put a mass of an electron into all the stuff we did up above and recalculate B and see if it's bigger or smaller. Or you could try to reason it out. Well, first of all, we know that the mass of an electron is much less than the mass of a proton. So one would think if B is equal to mv over qr, if m is a lot smaller, v, q, and r being the same, then B would need to be a lot smaller. But V depends on the change in energy of the electron. Since its charge is the same as the proton, then change in energy will be the same. But the final kinetic energy, while it's the same as the proton, the mass is a lot smaller. Kinetic energy is 1/2 mv squared. So if kinetic energy change is the same, but m is smaller, won't this V be a lot bigger? And so if V is bigger, won't that mean that B has to be bigger? Well, let's find out. Rather than using numbers, I'll just put letters in. So if I solve this for V, keeping in mind that change in kinetic energy is Q times change in potential, that means the final speed is 2Q times change in potential over m. And since we have V squared here, all that's under a square root. So if I put this back in here, we have m times square root of 2q delta V over m all over qr. Here is where the m shows up. 2 and q and delta V and q and r will all stay the same if we replace the proton with an electron, but m over square root of m would just be square root of m, and then we're left with 2q delta V still under a square root here, divided by qr. Yeah, I could simplify the square root of q over q, but that's not going to change. It's just this square root of m here in the numerator that gets smaller if the mass of an electron is less than the mass of a proton. So because this is the only place the m shows up, and it's in the numerator, if I make m smaller, the value of this whole thing is smaller, which means we need a smaller b. So to have the same trajectory, we need a much smaller magnetic field magnitude if we use electrons instead of protons.